Good morning, class. This is the lecture for the class on September 22nd. And we're going to first go over homework 2, which you should have turned in this morning. Today is Monday, September 21st, so like usual, I'm doing the video a day ahead of time. And so we'll be using the projector, and I'll be trying to keep the focus going here, so let's keep going. So the first problem was very simple. We have a sailboat, which a lot of people are familiar with, and so basically, some boat with a sail, and this problem is it can be very complicated because the direction of the wind can be in a different direction in the direction of the motion, and you know how to deal with that. But I made the problem very simple. There's a velocity of wind in the area of a sail, and that's providing power to move the boat. And as we went through, the power per unit area in wind is given by the density of air times the velocity q divided by 2, 1/2 rho v cubed. And so this is very simple. You just multiply times the area. And so you have to make a simple conversion. Most people are used to thinking about miles per hour, at least in this country. And so a good thing to remember is that there's 5,280 feet in a mile. And so 10 times that is the feet per hour. And that converts, divided by 3,600, into 14.67 feet per second. And then you just look up the conversion to meters, and it's 4.47 meters per second. We went through in another lecture the density of air, which you could have looked up, but a cubic meter of air is 1.2 kilograms. And so, the important thing also to remember here, and I really encourage you to always go through your units to make sure that you have that right. This is it's supposed to be watts joules per second, and so you want to use MKS units here because kilogram meter squared over second squared is joule. So everything has to be converted to MKS, and the result is 482 watts. Which, if you look up in your notes, 746 watts is 1 horsepower, so that's 0.65 horsepower. So that's the equivalent motor size being delivered to the sailboat. And I guess I don't have a good feeling for, I'm not a boating person, but I imagine a motorized boat might have a motor with a lot more horsepower than that. That's sort of interesting. But that's, the answer straightforwardly of how much power is delivered to the sailboat. Now, okay, well, that's all I had to say about that. And maybe during the chat class tomorrow, we can ask more questions about that. Okay, and the next problem I thought was kind of fun, and I was thinking about trying the experiment. I need to get a syringe from the lab somewhere, and I was thinking of doing it. If you, well, let's go through the numbers and then we can talk about. So this is basically taking a cylinder, and of course it has to be closed at the end. And I'm gonna draw it. I'm not gonna draw, putting the plunger in. But basically, the idea is that if you put the plunger right there at the top, and just stick it in a tiny little bit, okay, the air in there is still at atmospheric pressure because you haven't done anything yet. And then you push the plunger down. Okay, let's just make our plunger into a little cylinder here. Okay, and you push it down, holding down the plunger, so that this space is then, I used 1 centimeter. Now the cylinder itself is 10 centimeters. So once you're holding it there like that, as long as the cylinder hasn't leaked anything up the side, the pressure is P atmosphere times, and I'm gonna write this as V1, and the volume of the cylinder is V2, and so basically that's 10 P atmosphere. Because V2 over V1, so the reason why I'm writing 1 that way is because the way to think about this problem is that, okay, you've done this and you're holding it down, and that's the starting point of your experiment. And then what happens when you let it go is that pressure pushes the cylinder up until this point reaches the top here. And while that's moving up, the energy is the integral of P dV, as we went through, because P dV is the same as F dx, because P is per unit force per unit area, and so force per unit area times dV is force times dx energy. And now you can see why, you know, I set it up this way, because then you're going from V1 to V2, and of course P is a function of V, and so P is a function of V, and at V1 it's P atmosphere V2 over V1, and then as V changes, it goes as P atmosphere V2 over V, because for any volume along the length, P times V is equal to whatever P atmosphere V2. So P of V is equal to P atmosphere V2 over V. And you know how to integrate 1 over V, that's the logarithm of V. And so the answer is that the energy, you know, so basically this thing goes flying up, and when this bottom reaches the top of the cylinder there, it's converted all that potential energy of the gas compression into kinetic energy. And at that point, and so basically, let me okay, so I'm going to draw, at that point when the cylinder has gone up that high, all right, and it's winging, the kinetic energy is equal to P atmosphere V2 times the logarithm of V2 over V1. And so that's the way to think about it. At that point, okay, now there's no longer any PV or anything like that going on. It's basically, it's free of the cylinder, it's launched up and has a kinetic energy equal to that. And it's going to go flying up until all that kinetic energy is converted into potential energy with respect to gravity. And so it's just a matter of solving for H then. Plugging in everything. P atmosphere in MKS is 101,000 Pascal. And so the answer 23.8 meters. Now, that seems very high. I used 0.01 kilograms. Now that's the, I think the weight of like a plunger and a syringe. I was going to, at some point see if I could do the experiment. If any of you out there want to try the experiment, I'd be very interested in the results. If you have some syringe, of course you'll have to seal the end of the syringe. Don't put the needle on, but just sort of, I don't know, maybe glue the end so no air can leak out. And probably you'll have to put a little WD-40 in the cylinder so that plunger can slide very easily. And if anyone out there is going to try the experiment, and see how high it goes, I'd be very curious what the result was. But yeah, I ran my numbers several times, and yeah, 23 meters. It goes pretty high. Okay, so that was problem 2. So that was just kind of a fun problem to make you used to the idea of pressures and resulting energies and things like that. And now problem 3 is to calculate the energy released when we burn an alkane. And we'll be using that in today's lecture because we're going to start talking about petroleum. And petroleum is basically a collection of alkane molecules. So CnH, 2n plus 2 is an alkane. So basically it's C, however many there are. And there's an H on the end, and then there's H's all along here. An H there. All right, and you have to balance that equation, and so there's a few ways to do this, but the way I did it, and I'll refer to the I balanced this so I didn't have fractions. So I put 2 alkane molecules, and you'll see I'm going to have to divide by the weight of 2 of them. 3n plus 1 O2, 2n CO2s on the other side, and 2n plus 1 H2Os on the other side. And that's my balanced chemical reaction. And you can check that the number of carbon, hydrogen, and oxygen atoms are the same on either side. So that's what I wanted to do. I wanted you to set it up as a function of n. Now I know some students over the years have done it for each n, one after the other. It's kind of a pain then. It's much simpler, and what I wanted to do was to write it as a function of n. But if you write out for each n, like methane and ethane, etc., you can do the problem. It's just harder. Okay, so now basically, as I discussed, the energy released is the bond energies on the right minus the bond energies on the left. Meaning, in an exothermic reaction like this, where you're releasing energy, the products of the reaction are more tightly bound. They have more binding energy than the reactants. And that's a general principle I want you to be very comfortable with. That basically, anytime you go from one state to another, you release energy if the final state is more tightly bound. And the simplest example was, again, this piece of chalk. Okay, if my reaction is to drop the chalk, okay, it releases energy. That potential energy gets converted into kinetic energy, and the chalk earth system at the end of the reaction is more tightly bound because the chalk is down there. So, I mean, if you have to use that as an example to think about, do so. But But anyway, going forward then, so you have to count all the bonds. And so basically, on the, I did left first, okay, and there's N-1 CC bonds. That's from the alkane molecule. And so you can kind of see that because like here there's 4, all right, there's 1, 2, 3. And there's 2N plus 2 CH bonds. And where do I list the O2? Okay. Oh, okay. Okay, sorry, I didn't write it all out. Let's figure it out in real time. So here's my reaction, and so on the left-hand side, there's also these O2 bonds. Now we went through that those are double O bonds because there's 3N plus 1 oxygen molecules, and so each oxygen molecule contributes an O double O bond. And on the right-hand side, okay, there's CO2. Now, for CO2, you had to do the octet rule to figure out that that this is C double bond O. And so, since there are 2N CO2, there are 4N C double bond O from the carbon dioxide molecules. And then H2O is simply OH, and so there's 4 times N plus 1 OH bonds. And now there's a few ways to do this. Again, if you're more chemistry-like, I mean, if you like chemistry and you've gone through chemistry a lot, you can be very comfortable using energy per mole and things like that. I wrote up the solution in terms of the energy being released in electron volts, and there's a table in the notes giving you the electron volts of each bond. So for example, by the way, this should be 2. This is 3.6 eV, and then the CH bond is 4.29 eV, and then the oxygen is 5.17, and etc. And so you write that up on on either side, and you take the oops, I wrote that wrong. Yes, okay, that's right. So you write down the energy on the left-hand side, on the right, and so the energy on the left-hand side, and this is the energy on the right-hand side, and you subtract that from that, and you get this 12.85 times N plus 4.15 eV is released upon burning 2 alkane molecules, because that's the way I set up my balance, is with 2. And if you set it up with 1, I mean, you'll get half that, basically. I don't know, I just didn't feel like doing fractional molecules. So, burning 2 CN H2N plus 2 yields 12.85 times N plus 4.15 eV. And now what I wanted was wanted the energy release per mass. And so you have to divide that by the mass of an alkane molecule. And an alkane molecule, the way you do that is by using atomic mass units. An alkane molecule has n carbons, so if you have 2, so 2CN, H2N plus 2, so that's 2N times 12 plus 2N plus 2 times 1, because hydrogen is 1 atomic mass unit, times an AMU. And you can look up an AMU is somewhere there. It's well, it's 1.66 times 10 to the minus 27 kilograms. So you need to take that, you need to convert the EV to joules and then to BTU, and then the final answer is this, 41,900 times N plus 13,500, that's your BTU, divided by N plus 0.143. And so then you generate your table. Oops. Let me see if I can slide this over a little bit. And so for the various values of N, that is the BTU per kilogram of those molecules. So N equals 1 is methane. So if you burn a kilogram of methane, you release 48,500 BTU. Now, you can use this then, and we'll talk about this in a little bit. So for example, at the bottom of the page there, I've run out of room here. So gasoline. Gasoline is about N equals 8. We'll talk about that in a second here. And so for N equals 8, it was 42,800 BTU per kilogram. And you multiply that times the density of, you can figure out the density of gasoline as 2.84 kilograms per gallon. If you have a gallon of gasoline, it weighs 2.84 kilograms. So if you multiply that and then you perform the conversion, you get that that works out then to 122,000 BTU per gallon. And so we're mixing units all over the place here, but we have to, because when you go fill up your tank, you measure it in gallons. So we have to be able to be fluent in all these units. Now, as we'll talk about today, diesel, which there might be a few of you there that have a diesel powered car, or know someone who does. Diesel is a higher N. And you'll notice from the chart that N, as N goes up, the energy per mass goes down. But what happens is that diesel is, do I have it there? Maybe up higher. But okay, I have it in. It's denser, and I forget the exact number, but maybe it says, somewhere around, gasoline was 2.84. Maybe diesel is like. So we'll put here 2.84 kilogram per gallon. diesel is, I don't know, I think it's around 3 kilograms per gallon. So even though diesel, which is like N equals 14, has a lower mass energy density, meaning it has less energy per mass of diesel, because it weighs more, it has a higher, and usually, I mean, these numbers vary a little bit, but usually for diesel about 134,000 BTU per gallon. So you see that just doing this simple chemistry and knowing the mass densities of these different petroleum products, you can figure out things like how many BTU to get out. So in your car, for example, when you burn a gallon of gasoline, it releases 122,000 BTUs of heat. And then we'll talk about later in the course how that heat is converted into motive work, basically, to move your car. Now, you see, so you can figure out already that diesel has a higher volumetric energy density, and it's roughly worked out in the last 10 or 15 years that if you notice, diesel is a little bit more expensive than gasoline usually. And it sort of works out almost exactly that ratio. And that's also a main part of the reason why diesel vehicles are more efficient, because it's simply because diesel has more energy in a gallon of it. All right, and before we leave this and start going through the material, okay, N equals 1 is a special case. That's methane, CH4, and natural gas is kind of around 99% methane, and maybe like 1% ethane. And so for N equals 1, the chart up there says 48,500 BTU per kilogram. Now here we use a different volume unit. We use cubic feet. The density of methane is 0.656 kilogram per meter cubed. So that's kind of, it's fun to remember these various units and conversions because you remember the density of air was 1.2 kilograms per meter cubed, and so you see that methane is lighter than air, 0.656. Anyway, you perform those conversions, and the result is that you get that the volumetric density of natural gas is around 1,000 BTU per cubic feet. And that's, that's kind of handy to know that conversion. Because, for example, if we go to our main chart, which you can't read, let me make it bigger. Okay, you still can't read it, but I can read it here. So we used 32.1 quads of natural gas in 2019. And so you can convert that to cubic feet because you have 1,000 BTU per cubic feet, right? And one quad is 10 to the 15 BTU. So so basically one quad of natural gas is equal to 10 to the 15 quads, just put a Q there, over 1,000, yeah, 10 to 15 BTU, divided by 1,000 BTU per cubic feet. Right, 1 quad of natural gas is 10 to the 15 BTU divided by 1,000 BTU per cubic feet. So it's equal to 10 to the 12 cubic feet. And so when we said that we burnt 32.1 quads of natural gas, that was 32.1 trillion cubic feet. And we usually call this trillion cubic feet in some way with a T. And you'll see that there's other units and Roman numerals come in a little bit, or letters. But basically it's sort of a handy thing that it works out this way, because then you can directly make those conversions between quads and cubic feet. And we'll talk about this more as we go through the lecture today on natural gas. Okay, and that's the homework, and so that should have, the third problem should have primed you to, the next thing we're going to do here, which is we're going to talk about this stuff. And, as we've gone through, more than 80% of our energy comes from this buried chemical energy. And so we have to spend a lot of time talking about it and understanding it. So, petroleum. Petroleum, which, you sometimes call oil. Starting with it, natural gas is catching up, but petroleum is still the biggest at 36.7 quads. And as you see, that 36.7, there's a fair bit of it that goes into industrial processes. That's primarily as chemical feedstocks, but the majority of it as a fuel goes into transportation in our vehicles. So let's talk about petroleum. Now, this course may you may have taken this course because you're interested in solar or wind or a smart grid or these advanced energy concepts that we're working on today. But the thing is that, 99% of our vehicles are, and when I say vehicle, I mean cars, trucks, airplanes, are powered by petroleum in one way or another. And so we need to understand it as well, because if you're saying that, okay, we're going to do solar and wind and electric cars, okay, first understand what it is you're proposing to replace, and then go from there. And the reality is that petroleum is a fantastic source of energy, and energy that's really easy to use. So let's start walking through this, and as we walk through this, we'll do a few little calculations to show why that is to a certain extent. Now, first, let's look at the alkanes. And here's the alkanes, and maybe I can actually draw here. Methane is 1. CN H2N plus 2. Methane is 1, ethane is 2, propane is 3. Okay, and you see on the right-hand side it has, oops, I gotta uncover a little bit here. you can see on the right-hand side, now my, now my numbers don't match. 1, 2, 3. Okay, you see on the right-hand side the melting point and the boiling point, and particularly here we're interested in the boiling point, and so the boiling point of methane is minus 164 centigrade, so at room temperature it's a gas. And so, you know, natural gas is gas. And as mentioned, natural gas is about 99% methane with a little bit of ethane mixed in. And then we get the propane. Okay, and propane is kind of interesting, C3H8, because of course you're familiar with propane if you've ever had a barbecue and you've gone to fill the little tank that goes in the barbecue grill. The propane, its boiling point is minus 42 centigrade, which is pretty cold, and it's it is a gas, therefore at room temperature. However, those of you, okay, so it's a gas at room temperature, but if you go back to your chemistry, we're not going to go over this again, you'll remember that if you pressurize something, all right, you raise the boiling point. So under pressure, this is propane. Okay, under pressure, so this is atmosphere, but under pressure, it's a liquid. Because when you pressurize propane, you raise the boiling point up above room temperature. And so if when you go to fill your little tank for the barbecue, the tank you get it from and the tank you put it in are both under pressure. And if you take that tank and you can hear it sloshing around in there, it's a liquid. And then basically when you put it on the fitting going to the burner, as it's released into the atmosphere, it goes immediately to a gas because it goes up to atmospheric pressure or down to atmospheric pressure. All right, then next is butane, and I should have had as a prop here, but let me go get one. All right, so butane is in what's this thing, all right? See, everyone's familiar with a little lighter. And of course, it's a liquid in there. And as you see, butane is a gas right at freezing, right about at 32 degrees Fahrenheit. So at the temperature of this room right now, okay, I'm not going to flick it, but if I just let it go, you can hear it hissing a little bit. Actually, this I think is one of those safety ones that doesn't do that. But basically, it's a gas once it's released. But this this is under this whole thing is under very slight pressure, so that when it's inside the lighter, it's a liquid, and so you can hear it bouncing around because it's under pressure. But then once I release it, it's a gas. So that's pretty neat, actually. The concept of a butane lighter, it worked out just perfect. That butane is a liquid under very little pressure, but then a gas, and so it's perfect for a lighter. All right, and then we go on from there. Okay, and we're talking about petroleum today, so we want to get on to our next stuff here. And in particular, octane is C8H18, and you see its boiling point is way up there at 125 centigrade, or about 250 Fahrenheit or so. And then down here, you get to N equals 12, 14. That basically that's where around diesel is, and so those are always liquids. We don't try to pressurize them to do anything to them or anything like that. And as you can see over there, and so petroleum are basically these things from around N equals 5 to N equals 12, and petroleum stands for rock oil, and it's basically alkanes that are liquids at room temperature. And we've gone through what the great advantage of having an energy source that a liquid is. Now, let's jump ahead a little bit here and talk about what comes out of the ground. So, oh, I lost my focus. I'm trying to develop a technique for fixing this. I don't know why this won't work. It really vexes me. I mean, you know, it's like, okay, find the focus now. Why won't it do it? And I've learned that I can't switch cameras because then it really messes up. Come on, please. Please do it. Why won't she do it? Maybe if I do that and then cover it.